Hello everyone. In this video we will continue to examine topic 5.1 electric fields, and in particular we will continue to examine tricky example problems with Coulomb's law. Alright, so we want to use what we've learned in the previous video with reminding ourselves about how electric forces, and indeed forces in general, add vectorially to solve some tricky example problems with multiple charges. So let's start first with this particular problem. In this problem, two plus 10 nanocoulomb charged particles are 2.0 centimeters apart on the x-axis. What is the net force on a plus 1 nanocoulomb charge placed midway between them? What is the net force if the charged particle on the right is replaced by a negative 10 nanocoulomb charge? Okay, so visually, always want to draw a picture with this kind of thing, and we can see a little diagram right here. Take a look at Q1 and Q2. They're shown here. They're both positive, and our first question is, what is the net force on a positive charged placed right at the center? Note that if we draw our forces out, F by 1 on 3, charge 3, Q3 right here, and F by 2 on 3, well, Q1 and Q2 are the same size charge. They're both 10 nanocoulombs. And this distance is the same in both cases. So the distance between Q1 and Q3 and the distance between Q3 and Q2 is exactly the same. It's 1 centimeter, which means that F by 2 on 3 and F by 1 on 3 are the same length. They're the same size force. As a result, you add them up vectorially. So you draw one arrow and then you add them tip to tail. And because those forces are balanced, your net force is 0, which means Q3 does not feel a force or a net force right at that center. It's being pushed in both directions with equal magnitude. Now, in this second question, however, if you replace Q2 with a negative 10 nanocoulomb charge, now things are a little bit different. Now, that size force, F by 1 on 3, so that interaction between Q1 and Q3 did not change, but the interaction between Q2 and Q3 did change, but it simply reversed direction. The size of the charges will be the same. The distance between each charge and Q3 is the same, which means that F net is simply those two vectors added up, and those two vectors, F by 1 on 3 and F by 2 on 3, are the same size, which means if you can calculate one of them, you simply double it to get the net force on Q3, where Q3 is being repelled from Q1 and attracted by Q2. So we plug into Coulomb's law here. F equals KQQ divided by R squared. K is our typical K. Our Q's are given. And R is 1 centimeter here. So be careful. R is this distance or this one, not both together. And that 1 centimeter is written as 0.01 meters. You plug that in, you get a magnitude of force 9 times 10 to the negative 4 newtons. But there are two of this size force. There's F by 1 on 3 and F by 2 on 3. You get the same values for each. You add them up. So you simply double this number, and that gives you a net force of 1.8 times 10 to the negative 3 newtons to the right. All right. Next question. Adding electric forces in 2 dimensions. Okay, now we start to get to some pretty tricky problems. Okay, so 3 charged particles with these values here are placed as shown in this arrangement. What is the net force on charge Q3 due to the other 2 charges? Okay, we need to find the net force on Q3 due to the other 2 charges. So first, let's handle the direction. Think about what we expect. Q3 is going to be repelled from Q2 because they're both positive, and Q3 will feel a force on it from Q2 down and to the left. Okay, it'll be pushed away. Q3 will also feel a force due to Q1, but in that case, Q3 is attracted to Q1 because Q1 is negative. As a result, Q3 will feel force up and to the left. And so the net force that will be felt by Q3 is going to be those two forces added together vectorially. Okay, those two forces added together vectorially. We know, given the arrangement here, that because this is 5 centimeters and this is 5 centimeters, that angle theta here is 45 degrees. Same for this one. As a result, if you take a look at our forces, this positive charge at Q3 will feel a force up and to the left at an angle of 45 degrees from Q1, and Q3 will feel a force down and to the left at an angle of 45 degrees from Q3. And we can get that just by considering the diagram. If this is 5 centimeters and this is 5 centimeters, then that is a bisector and at a 45 degree angle. Now, okay, we want to break down the problem. Let us first consider how long these two arrows are. And to figure out those two arrows separately, we're going to use Coulomb's law. So Coulomb's law is F by 1 on 3 is equal to K Q1 Q2 divided by R squared. We plug in our K's and our Q's and our R. We attend to units, okay, so nanocoulombs in this case and centimeters. And we plug in to get a value of 2.7 times 10 to the negative 3 newtons. That is the length of F by 1 on 3. That is this arrow right here. Okay, we do the same for F by 2 on 3, and we find that because those charges are the same, this arrow is exactly the same length, and so you get the same value, 2.7 times 10 to the negative 3 newtons. So now we have the length of this arrow, this force right here, and this one. And what we want is the net force. But we can use little symmetry to make our life a little easier. Take a look at this. So the vertical part of both of those forces, F by 1 on 3, that's going to cancel out, okay? So this part is going to exactly cancel out with this part. And what's left is just the horizontal component of both of those forces. So the horizontal component of F by 1 on 3 and the horizontal component of F by 2 on 3, found here. Those are in the same direction and to the left. So those two added together, okay, whoops, should be the same size, will be our net force, and that net force will be to the left on Q3. All right, to find the values of those components, we use our trig. So we know that this angle is 45 degrees. We know this angle is 45 degrees, which means that the x component of those values are both negative 1.9 times 10 to the negative 3 newtons. Notice that comes about by taking that horizontal component here, taking the hypotenuse, 2.7 times 10 to the negative 3 newtons, and multiplying by cosine 45. We can then just straightforwardly double this value, negative 1.9 times 10 to the negative 3 times 2, and that gives us a net force in the x direction of negative 3.8 times 10 to the negative 3 newtons. Notice that the y values, because they're in opposite directions, one up and one down, they can be calculated, but they are going to cancel out, and indeed they do. Plus 1.9 times 10 to the negative 3 newtons minus 1.9 times 10 to the negative 3 newtons equals 0. So the net force is in the x direction, specified with a magnitude of 3.8 times 10 to the negative 3 newtons.